Hello YouTube, this is Eric from Coder Snacks. Today we're going to talk about big O notation. Let's get started. We've used big O notation a lot in these videos, and it's important to understand. It's a language many programmers use to talk about programs. During interviews, you'll need to discuss the big O characteristics of your code. This video will show you how. What is big O notation? It's a tool to describe characteristics of an algorithm. We want to know about runtime, memory usage, and other resource usage, like database calls or network bandwidth, as our input size gets larger and larger. We want to have a general idea, how much data can we reasonably run our program on? Billions of items? Millions? Hundreds? We care about data getting larger. If we have something that takes about log n operations, we can very quickly run it on billions of items. But if it's n factorial operations, we'll have a hard time running it on 20. This is the kind of estimation we want to be able to make. When we talk about big O, we're not being precise, we're approximating. Big O doesn't give us the tools to say that a program will run in 6 microseconds. We can use big O to say, given an input that's 10 times as large, this program will take about 10 times the time to run. Big O is fun, fuzzy math where being exact doesn't matter and we can hand-wave all over the place. Mostly. We're normally talking about the worst case or average or expected case, and it's a good idea to say which if it's unclear. We usually don't care about the best case, which is often O of 1, so be very clear if you're talking about best case. We're not going to dive into the formal definitions of big O in this video. Some people from academia are screaming to me about big theta and big omega at this point. To those people, in industry, we mean big theta when we say big O. We corrupted it. To not those people, please don't start saying big theta. No one will know what you mean. But to understand some rules for handling big O, we have to get a touch more formal for a moment. To say that some function f of n is, say, O of n squared, I should be able to pick two multiples of n squared such that one is below my f of n and one is above my f of n for large values of n. Let's say f of n is 5n squared minus 3n plus 7. I can pick 3 and 7, and we'll have a graph that looks like this. The red line is our function, the blue line is 3n squared, and the green line is 7n squared. At the beginning, the red line is larger for a little while, but as n gets large, the red line is always between the green and blue lines. We can say that our function is O of n squared. It's always between some two multiples of n squared. Can this work if f of n is n cubed? I want to argue that f of n is O of n squared, so I pick a huge constant, say 1,000,000, for the upper bound. But at some point, n cubed, in gold, is larger than 1,000,000 n squared, in black. No matter how large of a constant I choose, n cubed will be larger at some point. We can't say n cubed is O of n squared. This implies a few rules for dealing with big O. First, constants don't matter, and you can just get rid of them. Take some code that does a loop over n elements, then another loop over those n elements. Each loop is O of n. You could say that the code is O of 2n, but we don't care about constants. We would say it's O of n. We could pick constants that are twice as large to make the function fit our upper and lower bounds. Wait though, we're still kind of skipping a step here. We said n is the number of elements, but what are we measuring? Here we're measuring runtime. We have some operations in these loops that take a constant amount of time, and we're doing those operations n times. The exact constant time doesn't matter. We don't know if this addition takes 1 nanosecond or a quarter nanosecond or what, but we know that we do it as many times as we have elements. So we can say this runs in O of n time, where n is the number of elements in the list. By the way, there's a bug in this code. Do you see it? Pause the video if you'd like to look. 0 times anything is 0, so if we want the product of all these numbers, product should start at 1. In any case, this doesn't change if we clean up the code. Take a look at this version. You can't just count loops to see the big O of a function. Here, sum and reduce are both functions that run in O of n, where n is the size of the list you pass. So this similarly is O of n plus O of n, which, ignoring the constants, is O of n. Ignoring constants also means that the smaller terms don't matter. Take our example before, 5n squared minus 3n plus 7. As n gets large, the 3n and the 7 don't matter as much as the n squared, we can just get rid of them. Thinking about it another way, let's make the other terms as big as the first term. It still doesn't matter, they'd just be constants. As smaller terms, they matter less than that, so we can get rid of them. This means that when you add two terms with big O, the larger term is the only one that matters, and you can drop everything else. O of n squared plus O of n is just O of n squared. However, we can't do this when we multiply. If you have O of n squared times O of n squared times n is n cubed, so the new function is O of n cubed. If we apply this to code, when do we add and when do we multiply? In general, if we do something A, then something B afterwards, we add. If we're doing something A and for every element in A we have to do something B, then we multiply. Let's look at a couple brief examples. We've already seen an addition case. Here, we do the loop for sums, then afterwards we do the loop for products. This is an example of where we're adding runtimes. Let's look at a multiplication example. Here, n is the size of our multiplication table. We have our I loop, which is O of n, and we have another j loop, which is also O of n. For each of the I loop, we do O of n things in the j loop, so we multiply. For O of n times O of n equals O of n squared. For each of the inner loop, we do a print, and for each of the outer loop, we do a print. In the number of prints we do, this code is O of n squared. N squared for the inner loop prints, and n for the outer loop prints. So we have multiplication and addition here. But we're not done. We have O of n squared prints, but how much work is that print doing? It's hard to know, but a reasonable guess is that it's constant work to print a character. How many characters are we printing per print? The outer print is just printing a single new line, so that's O of 1. What about the printing of the number? We're printing the digits for n times n, which is approximately log 10 of n squared. So that sounds like log n squared work. But we can simplify this a little more. Log of n squared is 2 times log of n. And now we can drop the constants again. This is O of log n work per print. So if we're talking about runtime, this algorithm seems to run in n squared log n. The log n is multiplied too. Whew, that's a lot to work through. But it's a good example of how addition and multiplication work with big O. Next, if we have two different terms, we have to keep both unless we know something about the relative sizes of the terms. For example, this function calculates the sum of the products of each pair of numbers, then compares that sum to a list of totals to see if any of them match. If we say n is the length of the numbers and t is the length of the totals, the numbers loop is O of n squared, the total loop is O of t. For each element in totals, we're doing constant work. What happens when we add them? It's tempting to say n squared is second degree and t is first, so this is O of n squared, but that's wrong. N could be a few elements and t could be millions. They're not related to each other, so we have to include both. This code is O of n squared plus t. By the way, the runtime of this code can be improved. I'll leave that as a challenge for you. Here's another example which is more realistic and common. Let's say you have two strings and want to see if they have any characters in common. A naive way of doing this would be to loop through both strings and compare pairs of letters like this. This is O of st, where s is the size of one string and t is the size of the other. It isn't O of s squared because of the two loops. One string could be far larger than the other. It's the same for the faster version of this as well. This code is O of s plus t, not O of s. Now that we have a basic understanding of big O, let's look at some common patterns that often show up in programs and their big O characteristics. In our Twosome video, we talked about a smaller problem called Twosome, where you find pairs of numbers in a list of numbers that add up to a target. Here's a naive solution where you can't use the same number twice. In this code, we have an outer loop that is O of n elements, then an inner loop that, for each element in the outer loop, looks at O of n elements as well. This code's runtime is O of n squared. However, there's a better version. It doesn't make sense to check both ij and ji pairs since this is addition. So here we can use the pattern we discussed in that video and start our inner loop at the element after the outer loop. This is faster, but for big O purposes it's still O of n squared. Why? There are a few different ways to think about this. Look at this 8x8 table of I and j pairs, assuming len of numbers is 8. If you visualize the pairs we're looking at, it looks like the upper right half of a square. If the area of half a square is about 1/2 n squared, then this area is O of n squared. Remember, constants don't matter, and 1/2 is a constant. Another way to get to the 1/2 constant is to note that we've gotten rid of about half the work. Before we were checking ij and ji, now we're only checking ij. Here's a more mathy way to think about it. Note that the first time through the loop, we're looking at n-1 elements. The second time is n-2 elements, then n-3, n-4, and so forth, until we're looking at 0 elements at the end. These sum to 1/2 n times n-1. We can get rid of the 1/2, it's a constant. N times n-1 is n squared minus n, and we ignore smaller terms. This sum is O of n squared. This kind of pattern shows up a lot in nested loops. Another common pattern involves recursing into smaller parts of arrays. Let's say we have an algorithm that searches the whole array, then half the array, then quarter the array, such as our selection rank algorithm in the median video. In that video, we explained that the worst case for this algorithm is O of n squared. But on average, we should recurse into a list that's about half the size each time. In this average case, we end up with a function that looks like n plus n over 2 plus n over 4 and so on. This is O of n. Why? Calculus can tell us that this sum is approximately 2n, but if you don't remember calculus, you can still see it this way. Take a pi, n is 1 pi. The next pi will fill with half of n, quarter n fills half of what's left, and an eighth of n fills half of that, and a 16th of n half of that, and so on. We never quite fill the second pi. The whole sum is about 2n, which is O of n since we ignore constants. Great, now I'm hungry. In a similar pattern, let's say we have some exponential problem. For example, this code to generate all the n-digit binary strings. Each time through the loop, we do double the work as the time before in terms of number of string concatenations. We have a function that looks like 2 plus 4 plus 8 plus 16 plus so on to 2 to the n. For similar reasons as the last one, we can see that this adds up to slightly less than 2 to the n plus 1. 2 to the n plus 1 is O of 2 to the n. Again, we discard the constant 2. However, the runtime complexity is slightly worse because the string concatenations are not constant time. In contrast to exponential time, some common algorithms also take log n time. The most common is binary search. Say you have an array of n elements that's sorted, and you want to find an element in your array. You start in the middle and see if the middle element is too large or too small. If it's too small, you go left, and if it's too large, you go right. Each time, we're effectively ignoring half of the array that's left. How many times do we have to do this? Log n. We're dividing the array in half in each step until we have one element left. This gives us the formula n over 2 to the x equals 1. To calculate x, the number of iterations, we multiply both sides by 2 to the x, giving us n equals 2 to the x, and then take the log of both sides. The number of iterations we expect is O of log n. This pattern also appears in looking through a balanced binary search tree for similar reasons. A final common pattern we'll discuss is algorithms that are n to the k. This happens when at each step in an algorithm you have a number of choices and you have to explore all of them. One example is game trees. If you want to explore k moves deep in a game position, and each move has n choices, or a branching factor of n, you have to check your n choices, then for each of those your opponent's n choices, then for each of those n squared positions n more choices, up to a tree that is k levels deep. This would be n to the k. This is a very common pattern in runtime complexity of trees. There are an infinite number of possible big O classes, but here are some common ones in order. If you'd like more examples of big O notation, I'll put some links in the description, and of course you can check out any of our other videos. Discussing big O runtime or space complexity of your solutions is very common in interviews or in discussing code. Next time, we're going to do another live episode. We found another interview question, this time from Career Cup. Here, there's a game where you have pots of gold lined up. Each turn, you take a pot of gold from either end, and then your opponent does the same, and you win if at the end you have more coins than your opponent. Write a function to see if you can win. This time, we'll do it in a plain text editor. Let's see if I get a working solution. I hope you got something out of this video. If you have any questions, comments, something I've missed, or problems you want answered or covered, let me know in the comment section below. And if you enjoyed this video and want to see more like it, it would be great if you liked the video, subscribed, or both. I really appreciate it. See you here next time on Coder Snacks.